Hello dear friends, welcome to a lecture of integral transforms. We are studying Laplace transform. In our last lecture we have defined Laplace transform and we have seen the existence theorem on Laplace transform. In this lecture we shall study Laplace transforms of some standard functions. Before considering these Laplace transform of some standard functions, we shall prove a linearity property which is also important. I have written the property here. The property is if f1t and f2 of t are two functions of t and c1 comma c2 are constants, then L of c1 f1t plus c2 f2t is equal to c1 L of f1t plus c2 L of f2 of t. So the Laplace transform of this combination of f1 and f2, c1 and c2 are constants, is equal to this c1 into Laplace transform of f1 plus c2 into Laplace transform of f2. So this is the linearity property and we shall prove it. So it is easy to prove. We shall have to use only the definition of Laplace transform and we shall write by definition. We have by definition of Laplace transform. See, Laplace transform of f1 of t is defined as integral 0 to infinity e to the power negative st into f1 dt. Similarly, we have Laplace transform of f2 of t is equal to integral 0 to infinity e to the power minus st f2t dt. Laplace transform for f1 and f2 we have written, but we want the Laplace transform of this linear combination of f1 and f2 and we use the same definition. So therefore Laplace transform of c1 into f1 of t plus c2 into f2 of t is equal to. Now see the definition how it is expressed, the Laplace transform I shall write here. This is equal to, for Laplace transform of f1 of t we have to multiply f1 by this kernel of Laplace transform. We have seen in our last lecture e to the power minus st is the kernel of Laplace transform. It remains same. The integral also is fixed from 0 to infinity and the integration is with respect to t. So f1 is multiplied by e to the power minus st and then it is integrated between 0 to infinity to get the Laplace transform of f1. Similarly, to get the Laplace transform of f2, it is multiplied, f2 is multiplied by e to the power minus st and then it is integrated between 0 to infinity or from 0 to infinity with respect to t. Similarly, we want to get the Laplace transform of this combination or this expression, then it can also be written as integral 0 to infinity e to the power minus st. In place of f1 and f2, here it is this function in bracket c1 f1 of t plus c2 f2 of t into dt. So you note this, we have used the same definition of Laplace transform to write the Laplace transform of this combination, linear combination of f1 and f2. This is linear combination, first degree terms, functions, and c1 c2 are constants. Now we have to evaluate this right side integral and we can use the properties of definite integral to evaluate the right side integral. So this is multiplied e to the power minus st and this function is multiplied by this kernel. So we can write this as, now see, it will be integral 0 to infinity e to the power minus st into c1 f1 into dt and plus the integral or plus e to the power minus st c2 etc. So it is only the part of simple property of definite integral, and first we can write it as integral 0 to infinity e to the power c1 e to the power minus st into f1t plus C2 into e power minus st into f2 of t. And so after multiplying this, we can write the integration is with respect to dt. Now further we can separate the integral by using the property of definite integral. Integration of f of x plus g of x dx is integration of f of x plus integration of g of x, and that means integration of first plus integration of this second function. And while writing these separate integrals, we note that c1 and c2 are constants, and therefore these can be written outside the integral, and this we can write as c1 integral 0 to infinity e power minus st f1 of t into dt, plus similarly we can write this constant outside the integral. We have separated the integral. This is a property of definite integral. C2 integral 0 to infinity e power minus st f2 of t into dt. So thus we have used the property of definite integral to separate it. Now what is this? This is exactly the Laplace transform of f1 function, and therefore this is equal to c1 L of f1 t plus c2 Laplace transform of f2 of t. And this is what actually we wanted to prove. So this proves the result, or we may write this as 1 and 2, and we can write this as by 1 and 2, and this proves the result. See the left side is this L of c1 f1 t plus c2 f2 t, and the right side is c1 Laplace transform of f1 plus c2 Laplace transform of f2, hence the proof. So simple property we have proved, which is known as linearity property, but it is important. Now we shall obtain the Laplace transform of standard functions. So what is to be noted in this property, linearity property, is whenever there is a combination of two functions whenever there are constants, we can write constants outside the Laplace transform. C1 is written as outside the Laplace transform, C1 into Laplace transform of f1, plus it can be separated, and while separating the constants can be written outside the transform. So Laplace transform is expressed in terms of definite integral, and therefore the properties of definite integral can be used here for the linearity property. Similarly, C2 can be written outside the Laplace transform, and we can write Laplace transform of f2. Whenever there is a negative sign, we have to write the negative sign here. So this property can be used in this manner. Now we shall find out the Laplace transform of some standard functions. First we shall consider f of t as 1. So Laplace transform of standard functions, first L of 1, and this we shall show that it is 1 upon s. S is greater than 0 here, we shall assume, and the proof for this is we have by definition L of 1. See, here is the definition. L of f1, Laplace transform of f1 is integral 0 to infinity e power minus st f1 t dt, and here f1 is 1, so therefore this will be integral 0 to infinity e power minus st into f1 here is 1, so therefore into 1 dt, using the definition, by definition, and thus L of 1 is integral 0 to infinity e to the power minus st into dt. Now what is the integration of this exponential function? We can write it directly, that is e power minus st divided by coefficient of t, that is minus s. This is the integration with respect to t, and therefore it is e power minus st divided by minus s. Now if you put the upper limit here, we have to put the upper limit first, and the upper limit is infinity. that is the value of t. T is infinity, then it is e to the power minus s into infinity, or in the limiting case, and lower limit is 0, that is t is 0. So we shall see this first is when t tends to infinity, this term tends to 0. How we shall see here? Since limit t tends to infinity, e power minus st. So this will be equal to e power minus infinity. When t is infinity, minus s into infinity is again infinity, minus infinity, and 1 e to the power negative infinity will be 1 over e to the power infinity, and this will tend to 0, because whenever the denominator is infinite, the value approaches towards 0, and therefore because of this term is 0, the upper limit value is 0. So every time whenever we came across with this type of term, the e to the power negative infinity term, it is approaching towards 0, or its value we shall consider as 0, and therefore the upper limit for this expression is 0 minus. Now this value t is 0 means s minus s into 0 will be 0, e to the power 0 divided by minus s, and you see, so this is minus of minus becomes plus, and e power 0 is 1, and therefore this is 1 upon s, and this is our first standard formula. L of 1 is 1 upon s. Now we shall consider the next one as Laplace transform of t power n. Second, this is equal to gamma of n plus 1 divided by s power n plus 1. So this is gamma of n plus 1. Gamma function we have studied in separate lectures, beta and gamma functions. Special functions are these, and it is expressed in terms of gamma function. And condition here is n is greater than minus 1, because for negative values gamma function is not defined. We shall first obtain this result, and then we shall see what is the exact meaning of or definition of gamma function. The proof for this is, we have by definition of Laplace transform, L of t power n is equal to integral 0 to infinity e power minus st into t power n into dt. We are using the definition of Laplace transform, so that is to be noted. We have written earlier here also in linearity property, but I shall write this again. This is the definition of Laplace transform. L of f of t is integral 0 to infinity e power minus st into f of t dt. And changing this function f, we are obtaining the Laplace transform of different standard functions. So here f of t is t power n, and therefore integral 0 to infinity e power minus st into t power n dt. Only this function changes. This function changes, this integral and the kernel remains the same. So this is equal to, further to obtain this integral, we shall make use of a substitution. So we assume this st is equal to x. Put in this integral, put st is equal to x, and therefore t will be x upon s. Now what is dt? And therefore dt will be, because we are changing dt to dx, st is we have substituted as x, so dt will be dx upon x, dx upon s. This is the value of dt. And what about the limits? The limits when t tends to 0 or t is 0, x is 0, and when t tends to infinity, x also tends to infinity. S is assumed to be positive. And therefore, using this substitution in this integral, we have L of t power n, Laplace transform of t power n. The limits of integration remains same, 0 to infinity. E power minus st is x, and this is t is x upon s to the power n, and this dt is dx upon s. So this is the method of substitution we have used for this integral. It is easy. And now we shall see the integration is with respect to x, and these are the limits of x, and s is independent of the integral. We can write the s term outside the integral, and we observe that here it is 1 upon s to the power n. Power of s at denominator is n. Here the single power of s will be there, and therefore the total power of s at denominator will be n plus 1. And now the integral remains as 0 to infinity e power minus x, x power n into dx. So thus we have expressed the integral in this form, and now further that can be written as L of t power n is equal to 1 over s power n plus 1 integral 0 to infinity. We will write this in the form of gamma function, and that is a special function which can be written in this form n plus 1 minus 1 into dx, and this is exactly gamma of n plus 1, or that is equal to, this I shall write at numerator gamma of n plus 1, and this is the denominator, that is s to the power n plus 1. So this is our formula for Laplace transform of t power n. Now what is the exactly the gamma function using this notation, gamma of n. Gamma of n is equal to, this is capital gamma and capital gamma n, or gamma function is defined as integral 0 to infinity e power minus x, x to the power n minus 1 into dx. And you see this is gamma of n, and here it is e power minus x is a fixed function here, x to the power n minus 1. In this form the power we have to write n minus 1 or some number minus 1, and that number we have written here as n plus 1 minus 1 because the power is n here, and therefore we have added and subtracted 1 to get this form. And if it is written in this form, then it is a special function which is gamma of this number, and here it is gamma of n plus 1, gamma of n plus 1 divided by s power n plus 1. So this is the Laplace transform of t raised to n when n is greater than minus 1. Now what happens if n is positive integer? If n is a positive integer, then gamma of n plus 1 is same as n factorial. If n is positive integer, then gamma of n plus 1 is equal to n factorial. So this part we have studied in beta and gamma function chapter, and therefore in this case if n is positive integer, then this formula becomes, then therefore gamma of or L of t raised to n is equal to gamma of n plus 1 is now n factorial divided by s power n plus 1 if n is a positive integer. So both the form we shall remember. Actually this is the main result, and if in case n is positive integer, then it takes this form n plus 1, gamma of n plus 1 is same as n factorial. So both these we should remember. Now it will be easy to use the results. So for example, if we have to find Laplace transform of t to the power 2 t square, then see here n is 2, which is positive integer, and therefore we can use this formula directly. That is n factorial means 2 factorial divided by s cube. N plus 1, 2 plus 1 is 3, or that is 2 divided by s cube. And if we have like this, L of t to the power say 3 by 2, then it will be, now here n is not integer, so therefore we have to use this formula, L of t power n, gamma of n plus 1 divided by s to the power n plus 1, and that will be gamma of 3 by 2 plus 1 divided by s to the power 3 by 2 plus 1, or that can be written as, the denominator will be s to the power 5 by 2, and numerator can be reduced using the property of gamma function, and that is 3 by 2. See, this is 3 by 2 into gamma of 3 by 2, and again gamma of 3 by 2 can be reduced. That is a property of gamma function, since gamma of n plus 1 is n into gamma of n. This is the property, and therefore further this further can be written as 3 by 2 into subtract 1 from this, 3 by 2 minus 1 is half into gamma of half, and again we know gamma half is root pi divided by s to the power 5 by 2, or finally it can be written as 3 into root pi divided by 2 into 2 is 4 s to the power 5 by 2, since gamma half is equal to root pi. These are some results we have used from gamma function. So how to use the formula, for that purpose we have seen these two examples. Now we shall consider the third result as Laplace transform of e power at. L of e power at, and we will prove this is equal to 1 over s minus a. Here s is greater than a, positive quantity at the denominator, and for this we shall use the same definition. Proof for this, we have Laplace transform of e power at is equal to integral 0 to infinity e power minus st into e power at dt, or this is equal to integral 0 to infinity. We shall take negative s common from this, and in bracket what remains is t minus a. You see, this is minus st and plus sa here, so this should be this is at, so t is not s but t is to be taken common with negative sign, and what remains in bracket is s minus a into dt. Now you check this, e power minus st and e power plus at. Now the integration formula is to be used for exponential function. So this is e power minus t into s minus a divided by coefficient of t. The integration is with respect to t, and therefore the coefficient of t is negative in bracket s minus a, and the limits are 0 to infinity. Now if you put the upper limit, as in earlier case, see if upper limit is infinity and these are the values of t, the integration is with respect to t, and then this becomes e to the power negative infinity. T is infinity, so therefore negative infinity will be the upper limit, e to the power negative infinity, and we know e to the power negative infinity is 1 over e to the power infinity, and that tends to 0. So therefore the upper limit's value is 0 because of this term, and this is equal to 0 minus lower limit. And now we see the value of t is 0. So therefore e to the power negative 0, or that means e to the power 0, divided by this negative sign is there, minus s minus a, putting the upper and lower limit, or we can see the upper limit tending towards 0. Now finally this is equal to, see, negative of negative will be positive, and this e power 0 is 1. So it is 1 upon s minus a. And this is the Laplace transform of e power at. So this is our next formula. Example can be considered as, for example, Laplace transform of e to the power 3t. Using this formula, what is the value of a is 3, and therefore the result is 1 upon s minus a, means s minus 3. So it is simple. The next result we shall consider the Laplace transform of circular functions or trigonometric functions, and that together we shall obtain the two results as fourth. Laplace transform of cos at. This is equal to s divided by s square plus a square, and Laplace transform of sin at. This is a divided by s square plus a square. These two results we shall prove at simultaneously, and for this we shall consider a identity which is, or we know that, or we have, e to the power I theta is equal to, exponential function is equal to cos theta plus I sin theta. I is imaginary root of minus 1, and this is the result we have to assume, or we have to consider. E to the power I theta is cos theta plus I sin theta, and therefore e to the power I into at, instead of theta we are writing at. So therefore the right side will be cos at plus I sin at. This is the identity. E power I at is equal to cos at plus I sin at. Now we take the Laplace transform on either side of this. So therefore L of e power I at is equal to L of cos at plus I sin at. And now we can use this formula on the left side. You see, this is L of e power I at. L of e power at is 1 over s minus a. Now a will remain the same. This can be written as a into it. So here in place of t, here it is I into t, and therefore the left side transform is 1 upon s minus what is in place of t, here it is it, and therefore s minus here ia, not in place of a. T we should have to fix, and in place of a, here it is ia. So please note this. So the formula is e power at. Here it is L of e power 3t. It is 1 upon s minus 3. Coefficient of t is to be subtracted from s at denominator. Coefficient of t is ia, and therefore this is 1 upon s minus ia is equal to. And on the right side, we shall have to use the linearity property. So we have Laplace transform of f1 plus f2, two functions, is equal to, or c1 f1 plus c2 f2. c1 here is 1, c2 here is I, and that can be written as, first as it is, L of cos at plus, now this is a constant, I is constant, so we can write this outside the transform, and L of sin at. So thus we have use this formula on the left side, and we have used the linearity property on right side. So if you want, you may write this as using L of e power at is equal to 1 upon s minus a on LHS, and linearity property on RHS. Now again on the left side we can simplify it. We shall multiply the numerator and denominator here by complex conjugate of this term, that means s plus ia, or if I multiply this by s plus ia, and the denominator will be, the denominator will be s minus ia, s plus ia. So that is s minus ia into s plus ia, and that is a minus b into a plus b formula, that is a square minus b square, or that will be equal to square of s minus square of I, using the formula. And but what is square of ia? That is minus I square. I square is minus 1 into a square, or therefore this becomes s square plus a square, and I shall write that term here, s square plus a square, and on the right side it is the same, L of cos 80 plus I into L of sin 80. Now we shall see, you should note what we have done here. We have multiplied the numerator and denominator by s plus ia, and then the denominator is written in this form. Now what we can do is we separate the real and imaginary part on the left side, and what is the two parts here, that is s divided by s square plus a square, and plus I separate, s the first part divided by the denominator plus I separate, and into a divided by s square plus a square. This is the left side, and the right side we will keep as it is, that is L cos 80 plus I L sin 80. And now what we can do is we shall separate or we shall equate when two complex numbers, this is a complex number because it is a plus ib, and this is another complex number, that is c plus id. So when the two complex numbers are said to be equal, if their real parts are equal and their imaginary parts are equal, and therefore this equality implies their real parts are equal, means this s upon s square plus a square must be equal to L of cos 80, and the imaginary part is a divided by s square plus a square, that must be equal to L of sin 80. So equating the real and imaginary parts. Parts on both sides, we get. Now I shall write in reverse way, that means interchanging the side. This is real part on RHS and this is real part on LHS. So we get L of cos 80 is equal to s divided by s square plus a square, and what about the second result, that is L of imaginary part, equating imaginary part. This is the imaginary part, part containing I is imaginary part, L of sin 80 or sin of 80 is equal to, and the imaginary part here is a divided by s square plus a square. So these are the two results that we wanted to prove, and thus we should remember this, L of cos of 80 is s divided by, see the difference in this. When there is a cosine term, the numerator is s, that is parameter of the Laplace transform, divided by s square plus a square, and whenever the Laplace transform of sine we have to consider, then at the numerator this coefficient of t, which is a constant, is the numerator, and denominator is the same as s square plus a square. So for example, what will be the Laplace transform of phi t, cos of phi t? L of cos phi t will be, using the first formula, that is s divided by s square plus phi square. A is 5, that is 25. And if you want to write the Laplace transform of sin t, sin a t, that is sin 2t, then a will be at the numerator, this term, that is 2 divided by s square plus 2 square, s square plus a square. So in this way we can use these formulae. Now one more we shall consider is the hyperbolic functions, and that is our fifth result, Laplace transform of hyperbolic cos at is equal to, hyperbolic cos at is equal to, and that is s divided by s square minus a square, and Laplace transform of hyperbolic sine at, and that is a divided by s square minus a square. So to prove these results, we shall use the definition of hyperbolic function. See, for this proof, we have by definition of hyperbolic functions. First we shall write the definition for hyperbolic cosine. Hyperbolic cosine of x is e power x plus e power negative x divided by 2, and hyperbolic sine of x is e power x minus e power minus x divided by 2. So this we have earlier studied, these hyperbolic functions, and we shall make use of these definitions to obtain this Laplace transform. Therefore, now what will be Laplace transform of hyperbolic cos at? Hyperbolic cos at. Now that will be Laplace transform of instead of x here is at, and therefore this will be e power at plus e power negative at divided by 2. Using this definition, in place of x we have written at here, and on the right side also. Now on the right side we can use the linearity property. So here this can be separated and the constant can be written outside. So that's why the linearity property is simple but important, and therefore the right side we can write as 1/2. Half is the constant L of e power at, and plus sign is there, yes, plus half, or half can also be taken as common, L of e power minus at, separating the functions, Laplace transforms, and that is half. Laplace transform of e power at is a standard formula, it is s minus a plus half, and Laplace transform of e power minus at, there is minus sign, therefore this will be plus, s minus minus a, that is s plus a, and we can take half common, and this can be written as half into bracket addition of these two, and while taking addition we shall take the LCM as their product, and their product will be s square minus a square, and at the numerator there will be the addition of s plus a and s minus a. So plus a minus a cancels, it remains 2s. You can check easily this addition of these two, and so this half and 2 cancels, and what remains is s divided by s square minus a square. So this is what is the Laplace transform of cosine, hyperbolic cosine of at. Hyperbolic cosine at is this one. So thus we have proved this one, and the second I shall leave for you to solve. Use this definition of hyperbolic sign, and there will be only the negative sign, and you see after subtraction, in subtraction this term of s cancels and a remains. So in place of s here it is a. So this is also an important formula. So thus we have obtained the Laplace transform of some standard functions, and also we have proved earlier the linearity property. Now how to use these formulae that we have seen after deriving the formula. Here also you see what will be the Laplace transform of for example Laplace transform of sine say 70, sine hyperbolic sine 70. Now this is this definition is to be this formula is to be used, and a here is 7. So this will be 7 divided by s square minus 7 square, which is 49. So in this way we can use the formula easily, and thus we have obtained the Laplace transform of some standard functions. One general example we shall have as a problem: find Laplace transform of L of say 3 e to the power 5t minus 4 sine say 60 and plus 3 hyperbolic cos 2t. Find Laplace transform of this. And now it depends on only on linearity property and standard formula. So the solution can be written as L of this is equal to L of 3 e power 5t minus 4 sine of 60 and plus 3 cos hyperbolic 2t. This is equal to, we use the linearity property, or linearity property can be extended for combination of more than 2 functions, 3 functions, n functions, and therefore what is to be remembered to use the linear property, we can separate the Laplace transform at the time we can write the constants outside, and this can be written as 3 L of e power 5t minus 4 is constant L of sine 60 and further 3 is constant, then L of hyperbolic cos 2t by linearity property. And further we shall use the standard formula. And now see for the first, what is L of e power 5t? L of e power 80 is 1 over s minus a. Here a is 5, and therefore that will be 3 into 1 upon s minus 5. The formula we have used. You should note which formula we are using on observing the form of the function. Now next is minus 4 L of sine 60, and here we have the formula for L of sine 80 is a divided by s square plus a square, and here a is 6 divided by s square plus a square means 6 square, and plus 3 into L of hyperbolic cos 2t, and for the formula of hyperbolic cos 80 we have s divided by s square minus a square, and a is here 2, so that is 2 square. So this is the Laplace transform using standard formula. This further can be simplified, and that is easy. 3 divided by s minus 5, this is minus 24 divided by s square plus 36, and this is 3s divided by s square minus 4 square. So in this way we have obtained Laplace transform of some standard functions, and earlier we have proved linearity property, and these formulae are important in all we have obtained, and we can use the linearity property for obtaining the Laplace transform of linear combination of functions. So the remaining part we will continue in our next lecture. Thank you.